We are MicroB Incorporated, and we're here to present to you about creating environmentally friendly microbeads from keratin and PHA. Here I have with me today our executive board. I'm Nicole Madden, our Chief Safety Officer, and we have Emily Chan, our Chief Technical Officer, Ashley G, our Chief Financial Officer, and Christina Ferrara, our Chief Operating Officer. And here's an outline of what we're going to discuss with you today. We're going to define what microbeads are, discuss the solution we propose to solve issues with microbeads, analyze the current market for microbeads, show you our process design, consider any health and safety considerations, show you our economic summary and our preliminary business plan, and lastly, conclude everything we've just discussed today. So what are microbeads? Microbeads are small microspheres, 5 millimeters at its largest diameter. They typically range from 1 micron to 1,000 microns. They're currently used in a wide variety of products, mainly for exfoliation purposes in a lot of toothpaste, face washes, and other products. Consumers enjoy the sensory feeling that these microbeads bring to these products, and that include exfoliation, and that is distinct to these beads. And these beads are typically made out of polyethylene or other petrochemicals. There are a lot of issues with microbeads that are currently on the market. First of all, they're non-biodegradable because they are made out of polyethylene or other petrochemicals, and these are non-biodegradable materials, and this increases the presence of plastic, polyethylene, in our environment. And these beads then pass through the filters in the water treatment systems, and this is releasing plastic, particularly into our aquatic environments. And these polyethylene or other petrochemical microbeads can absorb dangerous toxins, and they're roughly the same size as certain fish eggs. Therefore, fish in the aquatic environments can eat these polyethylene beads and absorb these toxins in the marine life, and then these toxins can be passed on to humans or even further wildlife down that chain. These microbeads are so detrimental to our environment that the Microbead Free Waters Act of 2015 was a bill that was passed, and this bill amends the Federal Food, Drug, and Cosmetic Act to ban these cosmetics that have these intentionally added plastic beads in them, and where these beads would be rinsed off down the drain from face washes, toothpaste, and other products, and have these polyethylene beads run down the drain and end up in our aquatic environments. This bill bans these cosmetics starting January 1st, 2018, bans the manufacturing of these cosmetics starting July 1st, 2017, and this ban is delayed by a year for any over-the-counter drugs that use these beads. And this bill was first introduced into the House in March of 2015. In December, later that year, it was passed and agreed in the House. A couple weeks later, passed and agreed in the Senate, and passed by unanimous consent. And then later, a couple weeks later, signed by the President and became public law.
So what is our proposed solution for these polyethylene microbeads? So our proposed solution is to make microbeads from chicken feathers. And so you might be wondering why chicken feathers? Chicken feathers are actually a very huge waste problem right now. As our population increases, we're also increasing our food consumption, especially poultry. And so poultry processing plants have a huge amount of waste from these chicken feathers, and right now the solution for those is to either burn them, incinerators, or bury them in landfills, or actually recycle them into a low-grade animal feed. And the problem with these methods of disposal is, one, it produces a lot of greenhouse gases from burning, also takes a lot of room in our landfills because when they bury them. So it's actually really desirable to maybe repurpose this large waste product. So we based our manufacturing of these microbeads on 3 different patents. So the first one is we're not actually taking chicken feathers and putting them in microbeads. We're actually extracting keratin from these chicken feathers, and feathers are a very good source of keratin. So in this first patent, it describes how to take these chicken feathers, process them, grind them up, and actually extract the keratin by separating the fibers and separating the feathers from the shaft and the fibers. Then next, we take these keratin that we extracted from these feathers, and then our second patent describes taking this keratin that we've extracted and making a polymer composite using various polymers that it describes in the patent. And actually, if you do this correctly and disperse keratin throughout the polymer with this composite, keratin actually imparts very good improved properties, including rigidity, strength, and toughness, which is something all that we want in our microbead product. So taking that polymer composite, we move on to our third patent, which is actually making the microbeads. And the polymer that we chose is polyhydroxyalkylonate, which compared to other biodegradable polymers, this polymer is ideal because it actually degrades in marine environments, unlike other polymers which are also considered biodegradable. They only biodegrade in landfills. So we chose the class, we call it PHA. And then we take this PHA and keratin mixture that we made and create them into microbeads, and Emily will go into more specifics on how we do that. So for our product specifications, we want our microbeads to hit certain specs. As Nicole stated earlier, we want to look at the size of our microbead. Microbeads are only considered microbeads if they're 1 micrometer to 1,000 micrometers in size. And then also we look at how spherical these microbeads are to get that exfoliation or sensory experience consumers want in our microbeads. And then looking at hardness, if your bead's too soft, it's not going to exfoliate and the consumer won't be happy because that's what they're looking for. And then obviously biodegradability, we want to create microbeads that are biodegradable because they are creating, right now the polyethylene ones are not and are creating this issue in the environment.
So now we're going to analyze our market. Since there's a definite need, we want to make sure that the market we're entering into is a good one for this project. So first off, who's affected? Currently on the market, there are over 3,000 products that contain microbeads, consumer products alone. And of the top 5 beauty brands, each of them have products containing microbeads. So of the top 5 beauty brands, which are Olay, Avon, L'Oreal, Neutrogena, and Nivea, they each have yearly revenues ranging from 11.8 billion to 5.6 billion per year. And so having a solution for these products that they have containing microbeads would be very profitable for us. Not only that, but the skincare market is one of the largest markets of the consumer industry. It takes up 35.5% of the total global market of consumer products. And between 2014 and 2019, it's going to grow by 1.3 billion. So creating a solution to increase the skincare market, it's not something that's going to go away. It's only going to increase with time. So we want to make sure that they can have as many products on the market with microbeads and selling. And an important note to notice is that 44% of consumers that are buying cosmetics products actually will buy a product based on its claims. So if we can have a product out on the market that has the claims of exfoliation, it is environmentally friendly, actually consumers will be more likely to purchase that product in the future. So to also look at the competitiveness of the market that we're entering, we performed a 5 forces analysis. So the supplier power is the power of the supplier to jack up the prices of what they're giving us. So for us, it's chicken feathers. And with our market, it's not very much power to the chicken farmers to jack up the prices. Since it's a waste product and they actually have to pay to get it removed currently, they don't really have much power with us to kind of increase that price for us. The determinant of the buyer power is how likely that the buyers are going to be able to jack down our prices. And since, as I said before, over 3,000 products on the market have these microbeads and all of them need a solution by 2017, and there are very few actual solutions for a company to use, they don't really have any leverage. We kind of have a monopoly on the situation, so they're going to have to go through us. And then the threat of substitution products is how else could a company do what we're doing in a different way, and right now they don't have a solution. They have polyethylene beads, and as we said before, they're going to be banned, so what they're using currently has to be found a completely different way, which is where we step in. And then lastly, the threat of new entrants. So currently there are a lot of threats of new entrants into our market. Since it's such a popular thing, the law was just passed recently. A lot of companies are looking for these solutions since they have a need to. But since we are so far along in our development process and our business plan, and we know what we're going to do and have our marketing already set up, we don't think that anyone can come into our market faster than we can, so we can provide the best solution as fast as possible, which is what companies will want. We also performed a SWOT analysis, which is our strengths, weaknesses, opportunities, and threats. So some of our strengths are we are biodegradable, which is a great feature. We use cheap raw materials, therefore we have low operating costs as well. We have a high production volume. We're hitting 1.4 metric tons per day and 466 metric tons per year. We use unique raw materials and a novel process, which is something that no one on the market can claim that they do as well. And then the best part is that we are similar to existing products, so there would be consumer isolation. So any consumer currently using the polyethylene microbeads probably wouldn't even notice if they start to use ours, which is really important in the cosmetic industry, that there's no isolation when switching. Some of our weakness is that there are a lot of new products that could be entering our market. There is large, high interest in finding a solution. Therefore, a lot of people are working on this, and a lot of other companies are trying to find a solution quickly. It is a very competitive market. This could be a weakness, but it also can be a strength, because a higher competitive market means we could have a higher price and a higher product yield. Another weakness is that we do have to perform some analyses to create different SOPs, which is standard operating procedures, on how to vary size, since if it's going to be a microbead inside of a toothpaste, it needs to be a different size than one inside of a face wash. So we need to create some of those SOPs before moving forward. We do have a lot of opportunities, though. Like I said, every product on the market needs a solution by 2017. They kind of can hold out for a little bit, but by the end of it, they're either going to have to take it off the shelves or find a solution, which is where our opportunity is. And although our target market is the cosmetic industry, we do have a lot of opportunities now that we have this environmentally friendly option to enter into new markets. So some other new markets could be fluid flow analysis. We can use our microbeads for that. So there's a lot of opportunities for us when being able to provide this environmentally friendly option for companies. And we're also able to create this new market demand for our products, since it is environmentally friendly, which no one has been able to provide before. And then lastly, some threats is that we could have competitors with similar products. There could be new government regulations. Kind of this new law happened very, very recently. There could be other ones where they control what anything is flushed down the drain, and that could affect us. And then there could also be changes in the chicken industry, which would affect our raw materials. But looking at this, we have a lot of strengths and a lot of opportunities, and we have very low risk weaknesses and very low risk threats. So our company and our market is great for us to move forward with.
So at this point, you might be wondering, so how exactly we're making our microbeads? So this brings us to our process design. So our commercial scale manufacturing process can produce 1.4 metric tons of microbeads in a day. Our process can be described in 3 major steps. So first, we want to clean and reduce the chicken feathers into smaller fibers. After that, we will mix the fiber with PHA and also introduce dichloromethane and 2% methyl cellulose. Lastly, we're forming the microbeads by solvent evaporation method, which we will evaporate the dichloromethane that we added earlier. So here are the raw materials that we needed for our process. They are chicken feathers, PHA, DI water, ethanol, dichloromethane, and 2% methyl cellulose. And we also have here is the amount of each material that we use per day, and also the cost in a year. So our final product will be 50% keratin and 50% PHA. However, when you look at our amount needed per day, you see that the amount of chicken feathers is double the amount of PHA. This is because we're only taking the fiber from the feathers and we're removing the quill of the feather. We're doing this because they have different properties, and at this point, we're only looking to utilize the fiber from the feathers. And as you might already notice, the chicken feathers is free to us. This is because we're just taking the feathers from chicken processing plants, so we're pretty much like doing them a service by removing their waste for them. So this is benefits for both parties. For the PHA, we're specifically using a type of PHA called P3HB, and we're sourcing this material from a Massachusetts-based company called Metabolics, and we're hoping to form a friendly working relationship with them in order to get our PHA and also explore other polymer options in the future. Ethanol causes the most in all our raw materials. This is because we're using a lot of it to wash our chicken feathers in the beginning of the steps. So going into the details of our process. So after getting the feathers from our suppliers, we are using 2 ethanol washes to sanitize and dry them. So after that, we will grind them to reduce them into smaller sizes. Then we're using a customized equipment called comb separator to separate the chicken feather fiber from the quill of the feather. This is because the fiber has a lot of the alpha keratin and the quill has a lot of the beta keratin. And these 2 types of keratins have different properties. So, for example, the melting point will be different, and so because of that, we only want to use the fiber at this point. And next we can see, this is a diagram explaining to you how the comb separator works. So when the fiber and quill grind mixture enters the system, the fiber will be combed by a rotary brushes and also the combs. So after that, it will pass through a vertical screen. And this screen is only big enough for the fiber to pass through and not the quill. So this is how we're separating the two, and this flow is forced by air pressure. So after that, after we have treated the fiber, now they're ready for mixing with PHA. So we're introducing PHA and mixing it with fiber at 190 degrees Celsius. The reason why we need to do this at such high temperature is because we want to melt both materials to allow for thorough mixing. After that, we are using dichloromethane as our solvent to dissolve the two chemicals. And after that, we will remove the insoluble particulates by soft filters, and then we will stabilize this emulsion by 2% methacellulose as our homogenizer. So after that, this emulsion will move into a mixer, and we will mix this at high, very fast speed with water. Because dichloromethane is insoluble in water, when we're spinning it at high speed, the dichloromethane will actually evaporate and forming the microbeads. So after the microbeads is formed, we're removing the water and other chemicals by centrifugation, and also we will dry and do a size selection at the end of the process. So here's a process flow diagram describing the equipment that we will need and also instrumentation that we have incorporated into our system. For each stream, we have created a stream table detailing the mass flow rate and also the components in each stream. And also, in order to completely understand our system, we have also conducted heat and material balances on each equipment. This will allow us to make sure that our system is safe and also that our system is producing the microbeads effectively. So after this, Christina will talk to us about the equipment that we're using in our system.
So as Emily said, we're using a lot of different equipment in our system. You can see from the process flow diagram. But we'll actually be having two identical lines within our plant that will be running at the same time and producing the same products. So that's why everything you see is in a multiple of two. Our main unit of equipment that we're using throughout the process and the many steps is mixing tanks, our largest being 12,000 gallons and our smallest being 400 gallons, which is a jacketed mixer, which is mixing and heating the PHA and keratin. As Emily said, we're also using a ball mill grinder and the comb grinder you saw previously. We'll be using rotary dryers to dry the microbeads and the feathers, and some other equipment on there as well, such as the agitators we didn't use. So when we were sizing the equipment, the most important thing was that we were sizing the wall thickness properly. So the wall thickness needed to be a certain amount to be able to withstand the pressure inside of the tank. So that was very important to make sure we have that right. And then another big factor is when sizing our dryer is that it can handle the 1.4 metric tons per day that it's going to be handling. So that's more based on the feed rate. So our feed rate for our rotary dryers is 0.144 kilograms per second. And there's some other specifications there as well. So for our plant, we're going to be operating on a 333-day per year schedule. We'll have 3 shifts, each being 8 hours. We're going to have 5 operators per shift that'll split the duties on the floor and in the control room evenly. We're going to have an engineer on site from 9 to 5, 5 days a week, but they will be available on call after hours in case any problems arise. And we'll have salaries being $80,000 for engineers and $50,000 for our operators. And if you can see on the right here, we have our shift schedule. So during the first shift is when the batch 1 begins on both lines. Second shift, batch 1 is ending and batch 2 is beginning. And then third shift is when batch 2 ends. So we want to make sure that we have our most skilled technicians operating on the second shift because that's when the most happens. They have to be able to handle when one process ends and a new process begins. So we want to make sure we have our most skilled workers at that time. And then we decided to have our plant location in Arkansas. And the reason we chose Arkansas is because it has 37 chicken manufacturing plants, 21 of which of those are actually slaughterhouses. So a lot of poultry feathers for us to get closely, and we can reduce the shipping costs of moving those. It also has the lowest property tax in the U.S. at 0.62%, in Sebastian County, where we're located, whereas the U.S. national average is 1.1%. And we'll be manufacturing in Fort Smith of Sebastian County, which is also housed to Tyson, Butterball, and OK Foods. And then the electricity in Arkansas is 8.7 cents per kilowatt hour. For processed water using cooling water, it's 2 cents per 1,000 gallons and 50 cents per metric ton. And the total utility cost, which is calculated, which is 40% of our equipment cost, is $4.7 million per year.
Next, we're going to talk about any health and safety considerations that were taken throughout this process, as health and safety is of the utmost importance for our product as well as our process. As mentioned, our product is comprised of keratin and P3HB, both very non-hazardous, very stable chemicals, non-corrosive, and safe for topical use for humans. And however, we also use ethanol, dichloromethane, and 2% methyl cellulose in water throughout our process. 2% methyl cellulose in water, also very stable, non-hazardous, non-corrosive, no health or safety concerns there. Dichloromethane, volatile material with a high toxicity, but low corrosion, non-flammable, and it will not end up in our product, so therefore that risk is mitigated there as well. Ethanol is a flammable liquid with a low flash point of around 17.8 degrees Celsius. However, through our failure mode effect analysis and our hazard operability studies, where the ethanol is being used, it will not reach temperatures that will create a dangerous process. And ethanol and dichloromethane, also two materials that can be harmful to the environment. However, they will be disposed of properly and or recycled throughout our process. And now for the health and safety of our product MicroB and complying with the FDA. The FDA's legal authority over cosmetics differs from that of soaps. So face washes are considered cosmetics, and therefore they don't require pre-market approval. And the FDA can jump in and perform tests if any problems do arise. However, we do not need to have any expenses to perform tests or trials for the FDA. And however, we see no foreseen issues with our P3HB and keratin microbead because these are both very safe and non-toxic materials for topical human use.
So next I'm going to economic summary. We performed an economic analysis on this whole project just to make sure it was actually viable. And so this is all very preliminary numbers. So first looking at revenue and production costs, our revenue is going to be $66.6 million per year. This is based off our pricing of $100 per liter of our microbeads. And then raw material costs, as Emily stated earlier, it's pretty low because we are getting our chicken feathers, which are the major raw material, for free. So that cuts down a lot on the raw materials. But however, for consumables, it's very high because we are consuming a large amount of ethanol throughout the whole process. And then finally, royalties. 2 of our patents are still under patent protection. And so we expect to pay royalties to the owners of those patents, and we estimate it to be about 5% of our revenues at $4 million per year. Next, looking at our capital costs of actually building our manufacturing plant. Our internal ISBL capital cost is right now it's just our equipment installation costs at $11 million per year. And then we have our OSBL, which is actually the facilities, which is about 30% of our ISBL cost at $3 million. And then because this is a very preliminary analysis of our economics, we have a contingency cost, which is about 40% of our ISBL, just to make if any design changes or equipment changes or anything happens, we have that extra money to have some buffer room. So that brings our capital cost to about $22 million. So then looking at our actual cost of production per year, how much we're actually going to be expending per year to produce our microbeads. Our variable cost, which includes our raw materials and consumables and things like that, it's going to be about $26 million. Fixed cost of production is going to be about $4.25 million per year, bringing us a total cost of production of $34.9 million per year. And then with our revenues of $66.6 million, we expect a gross profit of about $16.3 million.
And now, to conclude, we want to analyze if we met the needs of our problems and provided a profitable solution. Now, the need was that these current polyethylene microbeads on the market are non-degradable and harmful to the environment as they pass through our water filtration systems and provide and release toxins to wildlife while also increasing the amount of plastic in our aquatic environments. And also the higher need due to the bill, the Microbead-Free Waters Act of 2015 that was passed, creating this larger need for a market to find a solution for these 3,000 personal care products that contain these microbeads. And the solution that MicroB provided was microbeads that are biodegradable in aquatic environments that produce a comparable sensory effect to the polyethylene microbeads and can be immediately implemented into these personal care products on the current market. While we also utilize a large waste product of chicken feathers that would otherwise end up in landfills or while being disposed of release greenhouse gases, further helping the environment in that manner. And the science of creating these microbeads and this process is based off of 3 U.S. patents that utilize this novel technology. MicroB will create 1.4 metric tons per day, and that turns to 466 metric tons annually. And our product is of high quality and meeting certain specifications consistently with an average particle size distribution of less than 400 microns, specific range of roughness for exfoliation to be comparable to the polyethylene beads, Mohs hardness range of 3 to 4, as a shelf life up to 5 years dry before our customers put it into their products, and then 1 to 2 years in the product where it will be slightly wet. And our business plan and product is very profitable. Our revenue is $66.6 million per year with a gross profit of $16.29 million per year annually, and a very short payback period of only 1.2 years, and that is because of the utilization of the waste product that we get for free and selling in a market that has a very high demand as of right now.
So we do have some recommendations going forward. The first would be conduct experiments on the bench scale. Although there were some benchtop experiments conducted when creating the patents, we want to do our own in-house. And this would help us better have accurate ratios for our components in the process, and it could also improve the quality of our end product. We'd also want to conduct some pilot plant testing. That would help us more narrow down the timing of our process. Currently we have very generous timing of our process, but we think we could, with pilot plant testing, kind of decrease those numbers a little bit, and therefore we would even be able to increase our production per day. And then also performing pilot plant testing would help us negate any problems that could arise before full-scale production. So seeing what problems could arise potentially on the pilot plant scale will help our technicians be well equipped if it were to happen on the full scale, and even prevent it from happening on the full scale. We'd also want to explore some more uses of the keratin. So as we said previously, we're only using the fibers from the keratin and not the quill. That's due to the different types of keratin within the fiber from the quill. So we want to explore through other experimentation what the quill could be used for within our own products and processes, or if there's another market or another company that could utilize the keratin that we could get from the quill, and find other markets that could be useful in. We also have some cost-saving initiatives. The first would be to perform a recycle stream on the ethanol. We do use a lot of ethanol, as Emily said, for both of our washes, and since we also want to be as green of a company as possible, creating this recycle stream would also have more green practices within our plant, which is something we're striving for. We also want to create a more profitable relationship with the chicken farmers that we're taking their chicken feathers from. As we said previously, we're doing it for free right now. It's a no-cost thing, but it does cost them money to dispose of it any other way, so we hope to create a relationship where they would pay us to remove it from them, and mutually beneficial on their end. And we also want to explore some new uses of our microbeads in the market. As I said previously, we're focusing right now on our target consumer being the cosmetic industry, but there's a large market out there for the use of our microbeads, especially since it's environmentally friendly and customizable within our process. And we also want to do some quality assurance checking, so we want to create a schedule that would happen throughout the processing, that they would be sampling off different points of our process to make sure that the ratios are correct and that everything is within spec and how we'd want it to be. And we'd also want to create a standard operating procedure to approve a batch before it is packed and shipped, so that what our customer is getting is what we want them to have and what they need as well, and it's of our highmost quality.
So we're going to just extend some thank yous to a lot of people who helped us throughout this project. First, thanking Jeff Palumbo, who is our industry mentor for this project. He actually did a lot of guidance in helping us decide how we wanted to approach this problem, how we wanted to go about it, and also guiding us to make sure that we were actually approaching this the right way.
We also want to thank Dr. Webster and Dr. ChE for assisting us on our project and also for the guidance throughout the semester.
We also want to thank Dr. Eugene Sommerfeld, who is a friend of Jeffrey Palumbo's, our mentors, and who was introduced to us by our mentor, for taking time out of his treatment to provide us some knowledge about polymer processing, as he's an expert in polymers and material science.
And we also want to thank the Chemical Engineering Department for fostering our minds over these past 5 years, so we were able to create this comprehensive and complete project of our capstone.
Thank you for listening to our presentation. Any questions?
Okay, so the floor is open up for questions here. Anyone have any
I got
questions?
one. How does the cost of your microbeads compare to polyethylene beads?
Yeah. We looked at the current market of polyethylene beads and made our price comparable to theirs.
It's actually in some of the other markets. So for instance, as Ashley said, we're selling it for $100 a liter. And for instance, another product on the market sells for $100 per gram. So we're definitely very competitive in our pricing, and people will more likely pick us.
Any other questions? Okay, I have a couple questions. I heard that you're dealing with ethanol, and you said it's not a big problem. I'm paraphrasing quite a bit.
We mitigated the risk for ethanol where ethanol is used in our process. It's only used in the first initial steps of our process to wash the feathers, and where it is used, the temperatures are not going to reach the flammable limits of ethanol.
Where's the flammable temperature again?
18 degrees Celsius, or 17.8 degrees Celsius.
So you're going to do this under cold conditions?
No, there's a vacuum line and nitrogen line in our dryer, and so it's under safe conditions within the vacuum rotary dryer.
Using nitrogen?
Yes.
One of the things that caught my interest, you didn't have your slides numbered, so back on the price of your DI water, I couldn't see that very well. So I was curious what you picked for your number.
Way back here.
What's that number over there that I can't read?
To the negative fifth.
2 times 10 to the minus
5
5 per year?
year. In millions.
In millions.
In millions.
Yes.
Yeah.
Keep the units consistent.
Well,
It's like $20?
Yes, within our process, we're not really using much. It's all process water and city water.
You're using city water.
Mhm.
Where's that on that chart?
It's in our other cost evaluations.
How many gallons of water per ton of feathers, or how many kilograms of water?
I think it's more detailed in our design. I'm not sure of the number off our head. I know it's 1.5 liters per pound of ethanol, so I'm not sure about the water though.
PHA is poly.
Hydroxyalkanoate. And it's a class of, polyhydroxyalkanoates are a class of biodegradable plastics, but specifically we're using P3HB, which is poly-3-hydroxybutyrate. Due to the hydroxy group on it, it was best for our process, and it's one of the most common types of PHA on the market.
Yeah, so I guess my observation here is a little bit late, but I probably wouldn't have reported DI water when it's down in, I haven't figured out exactly what 2 times 10 to the minus 5 means. It looks like it's $20 per year, right? Someone do that. Who's your economics expert up there?
Well, it's 8 million per ton, 8 cents per ton. We're using only 8 metric tons per day.
Yeah.
And then the
Oh, that's true. So I think since we're only using the DI water at like the formation of the microbeads, which is where we introduce the water and spin it at high speed. So that's why we're not using that much per day. And
Not
then for the
usage,
washing,
cost, if I'm reading this right, it's $20 a year.
Yeah, but it's only 8 cents per metric ton.
So why include it on this table and then exclude your processed water, which I suspect is more than what you're showing me. particularly in Arkansas?
So I guess for this table, we're just hoping to show like the raw materials, which are the materials that are like will actually go into our product and not the other like because the process or the city water is just for washing purposes. So we have that in our complete economic analysis, but we did not choose to show it on here.
Why 200 proof ethanol?
So this number right here of 200 proof raw materials, there are for the two sets of ethanol, it's 95% and then 70%. So we're using this number right now we're going to dilute it in-house, but you need a high percent of ethanol because these are chicken feathers coming from processing plants, and we want to make sure they're completely sanitized, and ethanol is a good way to do that.
But you can get a little bit lower price because you get the azeotropic version, which is sterilized, clean, all those other words I heard you say. Paraphrasing.
Yeah, we did a worst case scenario analysis and our economics.
So that's $32 million. Huh?
Yeah, there's a large amount of ethanol that has to be used to sanitize these feathers.
What's your major raw material?
Well, yeah, a good portion of it.
Yes. Other than chicken feathers.
There's 2% methylcellulose in water. Tell me a little bit about that raw material. What's that all about?
Economically, where it's used in the
How's it
process.
used in the process? Why is it there?
Can you go to the PFD?
So we're introducing the 2% methylcellulose down there into our mixer, and
What's its purpose?
yeah, so this is to stabilize the emulsion that we form with dichloromethane and PHA and our fiber.
Shortly
Yeah,
after.
it's homogenize the emulsion.
Is this from your expert or
Yes.
It's based on
This
this
is based-
patent.
just from your patent? Okay.
They did suggest we could look into other homogenizer or other stabilizer for emulsion, but this is the one they suggest. And for
Okay.
yeah.
Any other questions? Thank you very much.